Covalent bonding part 2, turning chemical formulas into two-dimensional structural formulas, also known as Lewis structures. Let's start with a quick review. We're going to be dealing with representative elements in this video. Those are the elements from these first two columns and these last 6 columns on the periodic table. Remember that elements will change their electron structure through chemical bonding until they have an octet of valence electrons. Valence electrons are the outermost energy level S and P sublevel electrons. If we write the electron structure or electron configuration of the elements from this first column or first group, we would see that they all end with S1. That means they have one valence electron. In this group, all of the elements end with S2, so they have 2 valence electrons. Let's skip across to the other representative elements. In this group, the elements end with S2P1, that's 3 valence electrons. Here, S2P2, that's 4 valence electrons. In this column, S2P3, that's 5 valence electrons. Then S2P4, 6 valence electrons. S2P5, 7 valence electrons. And finally, the noble gases, S2P6, 8 valence electrons. Now remember, they already have an octet. That's why they are stable elements. So we can write electron dot models to represent those valence electrons. If we use the period 3 elements as we go across the periodic table through the representative elements, groups 1, 2, and 13 through 18, the number of valence electrons is 1, 2, 3, 4, 5, 6, 7, 8. These are the electron dot models for elements from those particular columns in period 3. Remember, the idea is electrons are negative and they will repel each other. So we want to make the electron dot model so the electrons are as far apart as possible. Consider these 2 sulfur possibilities, for example. All right, so let's get to how to construct two-dimensional structural formulas or Lewis structures given the chemical formula. 2 important points here. You need to start and end with the same number of electrons. So in other words, when we write the electron dot models for the atoms, and then when we're done and we have the two-dimensional structural formula for the molecule, all of the electrons have to be accounted for. So count the electrons at the beginning and at the end, and you should have equal numbers there. The law of conservation of mass says that electrons can't disappear into nowhere or appear out of nowhere. So we have to count the electrons. And number 2, atoms should have octets when possible. Remember that the octet rule says that atoms will be stable when they have an octet. However, remember that elements from groups 1 and 2 and 13 will be exceptions to the octet rule. Once again, this is group 1, this is group 2, and this is group 13. Let's look at a few examples for exceptions to the octet rule. Here we have group 1. An example would be hydrogen in the compound HCl. Hydrogen has 1 valence electron, chlorine has 7 valence electrons, and we can determine that again from their location on the periodic table. We connect the single dots and we see that hydrogen forms a single bond with chlorine. Remember that the 2 dots that are being shared can be represented as a dashed line, and that is the bond, the covalent bond. So this is a single covalent bond. If we count the number of valence electrons around the chlorine, we have 2, 4, 6, and remember that the dashed line is 2 electrons being shared, so that's 8. That's an octet around the chlorine nucleus. If we count the valence electrons around hydrogen, we can see it's only sharing those 2 electrons with chlorine, and it has no other non-bonding electrons. So hydrogen doesn't have an octet. Group 1 elements will not. They will be exceptions to the octet rule. Check out group 2, beryllium, for example, in BeCl2. Beryllium has 2 dots before bonding. When we connect with chlorine, it can share 2 and 2, so now it has 4 valence electrons around its nucleus once the molecule is formed, but that's still not an octet. Group 2 elements, like beryllium, are exceptions to the octet rule. And for group 13 are examples aluminum in AlCl3. Before the bond, it has 3 dots. When it makes a bond with 3 of the different chlorines, it now has 2, 4, 6 valence electrons around its nucleus. That's not an octet either. Elements from group 13, like aluminum, are also going to be exceptions to the octet rule. Okay, so there are two steps to find the two-dimensional structural formula, or the Lewis structure, if you know the chemical formula. The first one is to draw the electron dot model for all of the atoms in the chemical formula. And when you do that, you should try to look for symmetry. Notice that there's symmetry in nature. It's not universally true, but many times you can look at a flower and notice that the flower is constructed so that the petals of the flower are balanced, so that the stem of the flower doesn't lean one way or another. Or if you look at many trees, you'll notice that the way the tree grows, the boughs of the tree are balanced around the central stem of the tree so that the tree is balanced and won't fall over. So we see that symmetry throughout large-scale nature. If you go to a museum and look at a skeleton of a whale, you'll notice that there's symmetry in that skeleton. That symmetry very often carries to the molecular level. So, try to make molecules symmetrical if you can. Try to balance their structure. One really important point is that center atoms in a molecule will be the atoms that are least represented in the chemical formula. So in other words, they'll have the smallest number for the subscript. And if all the atoms in the chemical formula are present in equal number, then we're going to look for center atoms that have the most single electrons in their electron dot model. Once we have all of the electron dot models for the atoms written out, then we're going to connect the single electrons to make covalent bonds, and we're going to make connections in this order. Make single bonds by connecting single dots between center atoms and other center atoms, if you have more than one atom at the center of the molecule. Then make single bonds by connecting single dots between center atoms and outer atoms. Outer atoms are atoms in around the periphery of the molecule on the outside. And then make double and or triple bonds by connecting any remaining single dots. Once you have all the bonds drawn in, make sure that you draw in any non-bonding electron pairs. These would be also known as lone pairs or unshared pairs of electrons. And then make sure you check your work. Remember that the total number of electrons that you start with around the atoms should be the same as the total number of electrons that you end up with once you put the molecule together in a two-dimensional structural formula or Lewis structure. And you should have octets wherever possible, remembering that elements from groups 1, 2, and 13 are exceptions to the octet rule. So let's take a look at some examples. Consider H2O. We're going to put the oxygen in the center. Well, first of all, we should consider, how do we determine how many dots there are? Well, oxygen is in the column where there are 6 valence electrons. 1, 2, 3, 4, 5, 6. So oxygen gets 6 dots, and hydrogen gets 1 dot. We're always going to be looking at the periodic table to determine the number of dots. So since oxygen has 2 dots, actually, I guess first of all we can say, since there's 2 hydrogens and 1 oxygen, oxygen's represented in the least number. We're going to put the oxygen at the center. And the 2 hydrogens on the outside, and we're not going to put them on the same side. Let's spread them out, try to make it symmetrical. Connect the dots between the center atom and the outside atoms and represent those as dashed lines. It's incorrect to leave this as your structural formula. You shouldn't represent the bond both as dashes and as dots. You should represent it as a short dashed line with no dots connecting. The dashed line is representing the 2 electrons that are being shared. All right, so we started with 1 and 6 around the oxygen and 1 more, so that's 8 electrons. And we end up with 2, remember the dashed line is 2 electrons, 4, 6, 8 electrons. So our total electrons is okay. Notice that around the oxygen, there are 2, 4, 6, 8 electrons. And around each of the hydrogens, there's 2 electrons. Now, since hydrogens are from group 1, that's okay. They are exceptions to the octet rule. Note that two-dimensional structural formulas, or Lewis structures, do not show correct bond angle in 3 dimensions. But it's still best to keep electrons as far apart as possible. So we can't say that we have a 180-degree angle between these 2 bonds. That's not actually true. We'll take a look at 3-dimensional structures later on. Let's take a look at some more examples. Here we have Pi3 as our chemical formula. Since there's only one P, one phosphorus, we're going to put that phosphorus in the center. Notice that there are 3 individual dots around that phosphorus. And I can tell you how many dots there are around phosphorus by looking at it on the periodic table. It's in the column where there are 5 valence electrons. All right, so each iodine is going to have 7 valence electrons, and I'm going to put the iodines by the single dots on the phosphorus. I'm going to put the valence electrons in around iodine in such a way that the single dots are facing towards the phosphorus. So I can make a single bond here, and I'm going to do the same thing around this iodine. I'm going to put the single electrons in such a way that they are facing the phosphorus. Just makes it for a little bit more of a clean job when I have to connect the dots. So I can connect the dots here and here and here from the center atom to the outside. There's only one center atom there, so I don't have to connect dots between more than one center atom first. All right, let's rewrite that. We have phosphorus single bonded to 3 iodines. And notice that each of the iodines still has 3 pairs, or 6 non-bonding electrons. And that's true for each one of these iodines. And then last but not least, let's not forget that there's still a pair of non-bonding electrons on top of that phosphorus. So we started with 7 more is 14, 7 more is 21, and 5 from the phosphorus, that's 26 electrons. We should have 26 electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Notice that we have an octet around the phosphorus, 2, 4, 6, 8 electrons. The bonding electrons count both ways, and all the iodines are the same, so let's check out this iodine. 2, 4, 6, 8. So we have octets where we would expect them. We started and ended with the same number of electrons, and we have octets. Here's another example, SiCl4. There's only one Si and 4 Cl, so I'm going to know that the center atom is going to be the Si. Let's put the Cl's in such a way that they're aligned by the single dots around the Si. Now Cl, like iodine, is going to have 7 valence electrons. It's in the same column as iodine. Let's put in the 7 dots around each one of the Cl's, taking care to try to keep the single dot at the towards the silicon, facing towards the silicon. So it's worth your time to go slowly putting your dots in so that you can tell which dots are paired up. It can be a little bit tedious, but it's worth your time to do that correctly. All right, so now let's connect the single dots from the center atom to the outside atoms, and let's draw in our bonds. 1, 2, 3, 4 bonds to 4 different chlorines. And put our non-bonding electrons in. Notice that each one of the chlorines will have 6 non-bonding electrons. I'm getting a little bit sloppy here, like down at the bottom there. You got to be careful about putting your dots in so that you kind of really can't tell what's paired up anymore. So take your time when you're doing that. Okay, we started with 7 around each chlorine, so that's 7. 7 more is 14, 7 more is 21, 7 more is 28, and then 4 more from the silicon, so that's 32 electrons that we started with. To end it up here, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 30, 32. We started with 32 electrons, we end with 32 electrons. And let's see that we have an octet. Let's check this chlorine, and all the chlorines are the same, so we can just look at one of them. 2, 4, 6, 8, so there's 8 electrons there. And then the silicon, now the bonding electrons again count around both of the nuclei and the bonds, so it counts around, these bonding electrons count around silicon, so that's 2, 4, 6, 8. Remember, the dashed line counts for 8 electrons, so we have octets where we expect them. Let's do another example, Si2Cl4. So now we have 2 Si's and 4 Cl's. We'll put the 2 Si's at the center. To put the 4 Cl's in here, let's try to make it symmetrical. So I'm going to go here and here and here and here. Cl is going to have 7 valence electrons each, so let's put the single electrons all towards the center and put the other electrons around the Cl, so there would be 7 total. Around each one of the chlorines, 7 electrons. Now we have 2 elements at the center of this molecule. So connect the center atoms together. That's the first thing. Then connect the center atoms to the outside atoms. We're going to make single bonds here, and here, and here, and here. And now notice that we have 2 single electrons on each one of the silicons. So let's connect those. I'm just going to connect them like that. Sometimes you're going to have some curved lines, and you're going to have, some lines that kind of cut across. That's okay. We need to clean that up now when we draw the structural formula, or the Lewis structure. We have 2 pairs of electrons that are being shared between those 2 silicons, so that's a double bond, right? 2 pairs of electrons being shared. And then single bonds to each one of the chlorines. Now, previous to this video, we did a little bit of practice with this, so if you are confused so far, you might want to go back and watch that previous video. Put in all the non-bonding electrons, so each one of the chlorines would have 6. And let's do our count. Each one of the chlorines started with 7 electrons total, so that's 7, 14, 21, 7 more is 28. 4 from this silicon, that's 32, and 4 more from this silicon, that's 36. We started with 36 electrons. Let's make sure we have 36 electrons here in the molecule. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 30, 2, 4, 6. So we have 36 electrons. That's great. Notice that around this silicon, there are 8 valence electrons. 2, 4, this bond is 2 electrons, and this bond is 2 electrons, so that's 8 electrons. Same thing around that silicon, and each one of the chlorines, they're all the same. They have 8 valence electrons, 2, 4, 6, 8. So we have octets where we expect them. Check the total electrons and check for octets. That's how you know if you have a valid 2-dimensional structural formula. All right, now we have Si2Cl2. That's Si, silicon, and Cl, chlorine. So how do we know what's going to go at the center of this molecule? We have atoms represented in equal numbers here. Normally we've been saying that if you have an element that has a smaller subscript, that would be the central element on the molecule, but now we have 2 and 2. Well, now what we're going to do is consider each one of these electron dot models, which one has the most single dots. And it's the silicon. So let's put the silicons at the center. If we're going to connect the single dots, we want to connect atoms that can make the most single dots, or make the most bonds that have the most single dots to make those most bonds. So we'll put the chlorine on this side to try to keep it symmetrical, try to keep it balanced. So the first thing we do is connect the center atom to the center atom. Then we know that the molecule has to have all the atoms connected, so now connect the center atoms to the outside atoms. And now look for any other connections that can be made between single electrons. We could make a connection here, and we can make another connection here. So notice that's 3 pairs of electrons being shared between the silicons. When we draw the 2-dimensional structural formula, or the Lewis structure, that means there's a triple bond between the silicons and single bonds to the chlorines. Let's make sure we draw those non-bonding electrons in around the chlorines. And that's important so that you get an accurate count of electrons. So when we started, we had 7 electrons around this chlorine, 7 electrons around that chlorine. That's 14. 7 and 7 is 14. 4 more from this silicon, that's 18. And 4 more from this silicon, that's 22. So we should have 22 electrons when we do our count here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So we started with 22 with the atoms, and we end with 22 electrons in the molecule. Those are the valence electrons again. Let's look for octets. Around this chlorine, we have 8, right? 2, 4, 6, 8. Let me just circle that just to show that. And around this silicon, we have 8. Remember, the bonding electrons count both ways. 2, 4, 6, 8. All right, so this silicon's the same as that silicon. This chlorine's the same as that chlorine. We have octets where we expect. Let's check out this example, SiS2. So there's one Si, that means it's going to go in the center, and the 2 S's would be on the outside. S's are each going to have 6 dots. Now, I can imagine that some people might be looking at this and wondering, how do you know exactly how many dots they have again? Just grab my periodic table here. Take a look at that. All right, let's look at this periodic table. All of the elements from this column have 1 valence electron. All of the elements from this column have 2 valence electrons. This column, all the elements have 3 valence electrons, then 4, 5, 6, 7, 8. So in representing covalent bonding by drawing 2-dimensional structural formulas, it's relatively easy to determine the electron dot models, how many dots you have to put in around the representative elements from these 2 columns and these 6 columns. 1, 2, 3, 4, 5, 6, 7, 8 valence electrons around those representative elements. All right, let's get back to this example. So what we're doing here now is we are connecting single dots. So we're going to connect the single dots from the center atom to the outside atoms because we don't have more than one center atom here. So we can start connecting the center to the outside atoms, or the outer atoms. And now notice that we still have some single electrons to connect. Let's connect those 2 electrons. And we'll connect those 2 electrons. So now you can see that silicon has 2 pairs of electrons that it's sharing with the sulfur on the left, and 2 pairs of electrons that it's sharing with the sulfur on the right. Let's not forget to put those non-bonding electrons in here. We have 2 4 electrons, or 2 pairs of electrons around that sulfur, and same around that sulfur. Those are the non-bonding electrons. And that's where you can really get mixed up. You have to really be careful about being neat with your work so you can see where the non-bonding electrons are. Okay, let's do our count. We have 6 electrons around this sulfur, 6 more around that sulfur, that's 12, and 4 more around that silicon. 12 and 4 is 16 electrons. So around this molecule now we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. Notice that around this sulfur we have 2, 4, 6, 8 electrons, and around the silicon we have 2, 4, 6, 8 electrons. So we have octets where we would expect them. And of course, that sulfur is just like that sulfur. So it's a valid structure if you start and end with the same number of electrons, and if you have octets wherever possible. All right, let's take a look at NOCl. Notice that we have a nitrogen, an oxygen, and 2 chlorines. Or I'm sorry, and 1 chlorine. What's going to be at the center of that atom? There's 1 of everything. Notice that the oxygen has 2 single electrons, the nitrogen has 3, and the chlorine only has one single electron. So let's put the nitrogen at the center. Let's connect the center atom to the outside atoms. And notice that chlorine has no more single electrons. And oxygen has one more single electron, and so does nitrogen. So let's make another bond there. So what we're going to see is that nitrogen double bonds to the oxygen, and the oxygen is going to have those non-bonding electrons there. Let's remember to put those in. The nitrogen still has the non-bonding electrons on the top. And then it single bonds to the chlorine, and there are 3 pairs of non-bonding electrons. And again, sometimes those are called lone pairs or unshared pairs. So we started with 6 electrons around the oxygen, 5 electrons around the nitrogen, 6 and 5 is 11, 7 more electrons around the chlorine, 11 and 7 is 18 electrons. We started with atoms that represent 18 valence electrons. This molecule should have 18 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So the total number of electrons before and after bonding is equal. Let's look for octets. Around the chlorine, 2, 4, 6, 8 electrons. Around the nitrogen, 2, 4, 6, 8. Again, each dashed line represents 2 electrons being shared. And around the oxygen, 2, 4, 6, 8. The shared electrons can count both ways for octets. All right, so we have octets around all the elements where we would expect. Remember, once again, that elements from groups 1, 2, and 13 will not have octets. They will be exceptions to the octet rule. Just for the sake of argument, let's say that you tried to connect it with the oxygen in the center. You could make a single bond here. You could make a single bond here. And now we'd be stuck with 2 single electrons around the nitrogen and no other single electrons that we could bond to. So that just would not work out. Just a couple notes here. Ring-shaped molecules do exist, and mostly that's important with organic chemistry. But we're doing inorganic chemistry. Remember that organic chemistry is the chemistry of carbons, and we're doing chemistry that's not really carbon-focused. So consider this example, C2H6. This is known as benzene. In order for C2H6 to be put together, we could make a ring-shaped structure like this with alternating single and double bonds around the ring, and then all hydrogens attached to the carbons. Notice there are 6 carbons and 6 hydrogens represented there. Notice that every one of the carbons, and they're all the same, let's go stick around that carbon there, each carbon has 1, 2 single bonds and a double bond. Every carbon is that way. Notice that the hydrogens don't have an octet, but of course hydrogen is an element from group 1, and that would be an exception to the octet rule. Now, we're not going to be making any ring shapes, so do not connect outer atoms to other outer atoms. I want you to consider 2 possible structures for C2O2. One way you could connect it is you could make a single bond between the carbon and the carbon, right? Always connect the center atoms first. And then we could connect the carbon to the oxygen and the carbon to the oxygen. And now sometimes people would do something like this where they connect the outside atom to the outside atom. Can you see that we're going to get a ring-shaped molecule when we do that? Sometimes those are known as cyclical molecules. We could connect another bond there and another bond there, and our structure would look like this. Carbon, triple bonded to carbon, bonded to oxygen, bonded to oxygen, bonded to carbon. Now the oxygens would each have 2 pairs of non-bonding electrons around them. We could put them in there. And you can see everything has an octet. We started with 6, 6 more is 12, 4 more is 16, 4 more is 20. We started with 20 electrons around the atoms. In this molecule we have 2, 4, 6, 8, 10. Let's do it again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 20 electrons represented. Notice that each one of the carbons is going to be the same. So for counting an octet, that's 2, 4, 6, 8 electrons. And each one of the oxygens would be the same. So for counting an octet, that's 2, 4, 6, 8. So what would say that would be a bad structure? Well, the answer is if you study organic chemistry, you'll learn the rules about ring-shaped molecules. And in organic chemistry, when you take organic chemistry, you would learn that a right angle to a bond in a ring like that makes these electrons so close to each other that the electron-electron repulsion of those negative electrons makes that an unstable structure. Now that's something that you would learn if you took organic chemistry. So what we're going to do instead is say, just don't make any rings. Don't connect outer atoms to other outer atoms. All right, so what we can do instead is connect the center atom to the center atom. Always connect the two center atoms, or however many atoms are at the center first. Then connect the outer atoms together, to the center. And now let's look for more connections. Let's make another bond between the center and the outside here, and the center and the outside here. And then let's make another bond between the two center atoms there. So now what we get is carbon, double bonded to carbon, double bonded to oxygen on the right, and don't forget these non-bonding electron pairs. That's important when we're counting for total number of atoms and counting for octets. And double bonded to that oxygen on the left, and don't forget those non-bonding electron pairs. So once again, we started with 6, 12, 4 more is 16, 6 more is 20 electrons. Now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. So this is a more valid structure. And unless you knew the rules of ring-shaped molecules, you wouldn't necessarily know that. So we're just going to say don't make any ring-shaped molecules. Don't connect outer atoms to each other when you're doing inorganic chemistry. By the way, if we look for octets, the oxygens are both the same, 2, 4, 6, 8, and the carbons are both the same, 2, 4, 6, 8. So the oxygens and the carbons do have octets. All right, let's take a look at another note here. Sometimes more than one valid two-dimensional structural formula, or Lewis structure, exists. Sometimes you can have more than one correct answer. So one example would be with resonance. This is where the structures differ only in the arrangement of electrons. If you put together a two-dimensional structural formula for SO2, it looks like that. But then what says the double bond has to be on the left? You could put it together with the double bond on the right. And we would say that what we have here is resonance. These two resonance structures are actually showing that the double bond is either on the left or on the right. And the truth is that the double bond is actually delocalized, is the term we use. The double bond is both on the left and on the right. Now that's something that you would study with advanced covalent bonding theory. We're not going to deal with any resonance structures in here. So if there's more than one valid structure, that's okay. You should at least be able to find one valid structure. Another possibility where there's more than one valid two-dimensional structural formula is when the structures differ in both the arrangement of electrons and the arrangement of the atoms. So consider this is C4H10. Organic chemists would call that butane. If you have all of the carbons bonded in a row, that's one form of butane, C4H10. And another form would be if you have the carbons bonded with 3 in a row and then one branched carbon coming off there. You can count them up. There are 4 carbons and 10 hydrogens in either one of these structures. Again, these two structures differ not only in the arrangement of the electrons, but also in the arrangement of the atoms. And that would be a type of an isomer that exists. We're not going to be dealing with any resonance structures or isomers. One final note here, to make it more manageable, chemists often use some shortcuts. And there are lots of different ways that they can do that, but here are a few examples. Consider Cl2. One of the shortcuts you can use, instead of drawing the structural formula like this with all the non-bonding electrons in there, is to just draw the structural formula and omit the non-bonding electrons. So if you skip writing the non-bonding electrons, it just goes a little faster. So that's one shortcut you can use. Another one is that Let's say we have a carbon chain, a hydrocarbon, like that butane we were looking at. It's a lot faster if you just don't draw the hydrogens in there. So skip writing the hydrogen atoms in the hydrocarbon. There are lots of different shortcuts that chemists can use. While you're learning how to do two-dimensional structural formulas, though, it's not a good idea to employ any of those shortcuts. So what we're going to do is write two-dimensional structural formulas, or Lewis structures, including all non-bonding electrons. And if you understand what we did in this video, you should be able to do that for these 10 molecules. Bi3, MgBr2, NCl3, H2O, CH4, C2H6, C2H4, C2H2, CO2, and HCN. And this is what you should do to show your work. Take that chemical formula, each one of those chemical formulas, draw out the electron dot models for the atoms that are represented in the chemical formula. So in this example, we have 2 Si's and 2 Cl's. Now, I know that since there are 2 and 2, I have to look at the single electrons in each one, right? We're going to take the element that has the most single electrons, if the elements are present in equal numbers, and put the element with the most single electrons at the center, so these Si's will be in the center. Then connect the center atoms. Then connect the center atoms to the outside atoms, and we're always connecting the single dots only. And then, if you can, make more bonds. So we're going to make a double bond, and then one more, make a triple bond between those 2 silicons, so we end up with that structure. Count the total number of electrons before and after, and make sure that that's equal. And make sure that you have octets wherever possible. In other words, octets for all elements that are not from group 1, 2, or 13. Good luck.